Imagine looking up at the night sky dotted with billions of stars. What would we see? A faint afterglow, a whisper of energy from the universe's fiery birth. This afterglow, known as the cosmic microwave background radiation, or CMB. By studying this, scientists have pieced together a detailed picture of the universe's infancy. The CMB story is a testament to human curiosity and our pursuit to understand the universe. The cosmic microwave background radiation, often referred to as the afterglow of the Big Bang, is a faint glow of light that fills the universe. This light is not visible to the naked eye, but it can be detected by sensitive radio telescopes. About 13.8 billion years ago, our universe was born in a cataclysmic explosion known as the Big Bang. Around 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and neutrons, forming the first atoms. These photons, which have been traveling through the universe ever since, make up the cosmic microwave background radiation that we observe today. The cosmic microwave background radiation is often described as the oldest light in the universe. It is a snapshot of the universe as it was just 380,000 years after the Big Bang. By studying the CMB, scientists can learn about the conditions in the early universe. The CMB is remarkably uniform in all directions, indicating that the early universe was incredibly homogeneous. However, the CMB also contains tiny temperature fluctuations, on the order of a few microkelvins. These fluctuations, although small, are incredibly important because they reflect the seeds of the large-scale structures that we observe in the universe today. Think of the early universe as a vast, smooth ocean. The tiny temperature fluctuations in the CMB are like ripples in this ocean. Over billions of years, gravity caused these ripples to grow, eventually forming the galaxies, clusters of galaxies, and other large-scale structures that we see in the universe today. The CMB is a treasure trove of information about the early universe. It provides strong evidence for the Big Bang theory and has allowed scientists to determine the age, composition, and geometry of the universe with remarkable precision. Detecting the faint afterglow of the Big Bang was no easy feat. It required sophisticated instruments and a bit of serendipity. In 1964, two American astronomers, Arno Penzias and Robert Wilson, stumbled upon the CMB while using a large horn antenna at Bell Telephone Laboratories in New Jersey. They were initially puzzled by the persistent hiss of microwave radiation that seemed to come from every direction in the sky. After ruling out other possibilities, such as interference from pigeons roosting in the antenna, Penzias and Wilson realized that they had detected the cosmic microwave background radiation. Their discovery, which earned them the Nobel Prize in Physics in 1978, provided the first direct evidence for the Big Bang theory. In the decades that followed, scientists launched a series of space-based missions to study the CMB in greater detail. Two of the most important missions were the Cosmic Background Explorer, or COBE, launched in 1989, and the Planck spacecraft launched in 2009. COBE was the first mission specifically designed to study the CMB. It produced the first detailed map of the CMB's temperature fluctuations, providing strong evidence for the Big Bang theory and giving scientists a glimpse into the seeds of cosmic structure formation. Section 5. The secrets hidden in the CMB. The Planck spacecraft, with its superior sensitivity and resolution, took CMB observations to a whole new level. Planck's map of the CMB was even more detailed than COBE's, revealing subtle temperature variations that provided even more precise information about the early universe. These space-based missions, COBE and Planck, have revolutionized our understanding of the CMB and its significance for cosmology. The CMB is not just a uniform glow, it contains tiny temperature variations, often described as anisotropies. These anisotropies are incredibly small, on the order of a few millionths of a degree. Despite their minuscule size, these temperature fluctuations provide crucial information about the early universe. The pattern of these anisotropies reveals a wealth of information about the universe's composition, geometry, and evolution. For example, the size and distribution of the anisotropies tell us how much ordinary matter, and dark energy make up the universe. Section 6. A glimpse into the infant universe. Imagine looking at a baby picture of the universe. That's essentially what the cosmic microwave background radiation provides, a snapshot of the universe as it was just 380,000 years old. This baby picture tells us a lot about the conditions in the early universe. The CMB tells us that the early universe was incredibly hot and dense, 1,000,000,000,000,000,000 times denser than water. It also tells us that the early universe was remarkably uniform, with only tiny variations in temperature and density from one place to another. These tiny variations, though seemingly insignificant, were crucial for the formation of the large-scale structures we observe in the universe today, such as galaxies, galaxy clusters, and cosmic filaments. These variations acted as seeds for gravitational collapse, pulling in matter over billions of years to form the structures we observe today. The uniformity of the CMB also presents a puzzle. Regions of the universe that are billions of light years apart are so similar in temperature that they must have been in contact at some point in the past. The universe's baby picture, captured by the cosmic microwave background radiation, reveals its infancy. One striking feature of the CMB is its uniformity. The temperature is consistent with tiny fluctuations. This implies the early universe was incredibly homogeneous. To explain this, cosmologists proposed inflation. Inflation suggests the universe expanded exponentially after the Big Bang. This expansion smoothed out initial inhomogeneities. The cosmic microwave background radiation has profound implications for our understanding of the universe. It provides strong evidence for the Big Bang theory and has allowed cosmologists to determine the age, composition, and geometry of the universe with remarkable precision. By studying the CMB, we have learned that the universe is approximately 13.8 billion years old, much older than previously thought. We have also learned that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. Dark matter is a mysterious substance that does not interact with light, but its gravitational effects can be observed on galaxies and galaxy clusters. Dark energy is an even more enigmatic force that is causing the expansion of the universe to accelerate. The CMB also provides clues about the geometry of the universe. By studying the pattern of temperature fluctuations in the CMB, cosmologists have determined that the universe is very close to being flat. This means that the geometry of the universe is Euclidean, which is the geometry we are familiar with from everyday life. The cosmic microwave background radiation is not only a relic of the Big Bang, but it also provides clues about the future of the universe. The CMB tells us that the universe is expanding and the rate of expansion is accelerating. This acceleration is thought to be driven by dark energy, a mysterious force that makes up about 68% of the universe's total energy density. The fate of the universe is ultimately determined by the nature of dark energy. If dark energy continues to dominate the universe's expansion, as current observations suggest, then the universe will continue to expand forever. As the universe expands, galaxies will become increasingly isolated from one another, and the night sky will grow darker as distant stars fade from view. Eventually, the expansion of the universe will become so rapid that it will overcome the gravitational attraction holding galaxies together. Galaxies will be torn apart, followed by stars, planets, and even atoms themselves. This scenario, known as the Big Rip, is just one possible fate for the universe. The cosmic microwave background radiation reminds us that we are part of a vast and ancient universe. It is a humbling thought to realize that the light we observe from the CMB has been traveling through the universe for over 13 billion years, carrying with it the secrets of the universe's infancy. The discovery of the CMB and its subsequent study have revolutionized our understanding of the cosmos and our place within it. We now know that we live in an expanding universe that began with the Big Bang and that this expansion is accelerating. We have also learned that the universe is composed mostly of dark matter and dark energy, substances that we do not yet fully understand. The study of the CMB is an ongoing endeavor, and future observations promise to reveal even more about the universe's origins, evolution, and ultimate fate. As we continue to explore the cosmos, we are constantly reminded of the vastness and mystery of the universe we inhabit. The CMB serves as a constant reminder of our place in the grand scheme of things, a small part of a vast and ancient cosmos.